You know, if you, I think there are some, you know, unsolved mystery going on in your design, right? I know that from my, you know, past experience with this class. So, you know, if you have any question, probably we can take some time. If you have some specific questions, you know, you can ask. You know, we can spend some time to answer. Otherwise, we can move on. Don't be shy, right? You don't have to be shy, right? You are here to study, so. Any unsolved mystery you want to bring up? Okay, probably turn on microphone, right? It takes time to type, right? Turn on microphone and talk to me. Okay, I'll wait 1 minute, then no question, then move on. Okay. Okay. 10:33. Will we move on to cache? Okay.
Professor, I have a question. It's not directly related to the milestone, but I was just wondering if you still receive late submissions.
Yes, late submission will be received. Yeah. So you will get a lot of credit, actually, small penalty. I mentioned no rate turn in, right? But TA will receive. Right? TAs will still receive rate turn in, and you will get good credit if your things are working fine. So late submission is much better than no submission, right? Okay, thanks, Amy.
Thank you, Professor.
Professor, I have a similar question.
Okay.
I turned in incomplete assignments before the due date. Can I turn it in again if I complete the milestone?
Yeah, I think someone, are you there? That will be late submission, right?
Yeah.
So there will be small penalty again, but yeah, that is okay, still okay.
Thank you.
Any other questions? So if you look at, you know, fourth milestone, so I created humongous amount of data dependency, right? So check out this source. Yeah, I know it is hard because you are pretty new to hardware design, right? So you have to understand your clock and, you know, a certain clock cycle, right? So what should happen, right? So clock is running like this. This is a time, right? Time and time, right? Say this clock is 10 megahertz. I remember the clock is running at 10 megahertz, meaning clock period is 100 nanosecond f, right? Frequency. How frequent that is? This one is how frequent? 10 million pulses in 1 second. Anyway, so 100 nanosecond. The something should happen. Something should happen in this clock cycle, right? Data forwarding, for example, right? You're not supposed to cross the boundary like this. This is wrong, right? For example, execution stage to mem stage. You are not supposed to cross the boundary, right? So like this, execution, decoding, like this. This is wrong. Why? This is wrong. If I draw a schematic diagram for this red one, it looks like this. You have ALU, then flip-flop, okay, then flip-flop, okay, for source operand, then clock is common, right? Oops. Clock is common, battery is low, okay, that is that. So if you cannot hear my voice, please let me know. My headset says battery is low. Okay, I have to connect this guy. Okay. So what happens is, so if I draw that arrow in this schematic, so execution stage to execution stage, that means you are connecting like this. Execution stage output, this one, that output is connected to execution stage. So that is execution stage, right? Execution stage. Right? Then you are connecting like this or this. So within execution stage, right? Then this circuit is wrong. That is not synchronous sequential logic. It is asynchronous logic. Asynchronous. It is like this. If I draw, ALU is combination logic, right? So think about the replace ALU with, for example, AND gate, right? That is combination logic. Then you are doing this, right? You are essentially doing this operation, this, right? So very strange logic that output is directly connected to input and influencing this output again, and then you are feeding back, then influencing this one again, endless loop, right? Very strange logic. It is called asynchronous logic. So we are not dealing with that asynchronous logic, right? Synchronous, right? So if I draw this, then this output is connected to decoding stage, right? This one, decoding stage. So pipelining, implementing pipelining is a little bit hard if you are new to hardware design, but some experienced hardware designer, it takes no time actually. If you understand the principle, it takes I guess 2 hours to design this CPU. Okay, anyway, any questions? Today is going to be very uncomfortable. I have to pull this line. Okay. Yes, Q1.
교수님, 저희 이제 마일스톤 다음 거 할 때 그 리셋 관련해서 리셋 말고 먹스 쓰는 걸 권장한다고 하셨던 거로 기억하는데 혹시 저희 그 마일스톤에서 리셋을 건드리면 뭐가 문제가 생기나요, 이번에?
No, it's okay. So the question is it okay to play with the reset input in flip-flop? It's okay. The answer is okay. No problem. So
네,
Yukyun, why are you asking the question? Have you encountered any issue with that reset input?
그게 마일스톤 4 할 때 리셋을 건드려서 혹시 뭐가 문제가 생겼나? 제가 대충 헥스까지 숫자를 넣는 거 됐는데 보드에 숫자가 안 떠서 혹시 제가 리셋을 건드렸는데 리셋 건드린 게 문제였나 싶어서 여쭤봤습니다.
Yeah, so that would be not the issue, I guess. The reset, what is the purpose of using reset? If you supply one to, let's say, rising edge of the, assuming this one is synchronous, S-Y-N-C. I'm very bad at spelling. Synchronous, okay, synchronous resetable flip-flop. Meaning at the synchronous, meaning a flip-flop is working based on this clock, okay? So at the rising edge of the clock, flip-flop is checking reset signal. If the reset is 1, for example, like this, okay? Then that means you want to initialize this Q output to 0, okay? At the rising edge of the clock. If I draw some timing, detailed timing, okay? So rising edge of the clock, Q output, this Q will be like this, 0, okay? Assuming 32-bit, okay, 0. At the rising, if reset is asserted. In case of a synchronous resetable flip-flop. So you have to be careful if it is synchronous or asynchronous resetable, asynchronous resetable. Asynchronous resetable flip-flop has nothing to do with clock. So I don't care about clock. So when reset is asserted, output will be initialized immediately. When in case of asynchronous resetable, async, right? Synchronous clock, right? Asynchronous. So a Q is like this. Q is this, right? When reset goes up, then output is 0 after little delay, flip-flop delay. But it does not wait until clock is going up from 0 to 1. It doesn't wait until that clock goes up. So asynchronous. So in Verilog, how to implement that guy and this guy, that is in the book, right? If you use always at passage clock, it looks like flip-flop, right? Passage clock at the rising edge of the clock. This is passage, positive edge, right? Goes up. This one is negative edge, neg edge. In Verilog, NEG, neg edge, negative edge. So do something, begin and end. Do this. Always do this when at this time, at positive edge, right? So Q to D. Okay. So if I add reset signal, reset, then Q is 32 value 0, 32 bit. Otherwise Q D. That is synchronous resetable flip-flop, right? So it is waiting for clock edge, waiting for that clock edge. Then reset, is 1, then do this, right? So that is synchronous resettable flip-flop. Then how to implement asynchronous? Simple. Same thing. This body is the same, but always is different. Always at pass edge clock. That is a trigger condition, right? Trigger, right? When clock goes up, then do this. Trigger, right? Trigger condition. And you have one more trigger condition. For example, pass edge reset. It's a pass edge reset. One more. So either this or that, right? Trigger point. That is asynchronous, right? So body, this one is the same, but always is different. Q1, there is some more detailed explanation. So I guess in our, I don't know, our skeleton, this is the one or this is the one? Okay. 어디가 잘못됐는지 모르겠네요. PC만 4씩 증가하고 나머지는 전부 0으로 나오고 있습니다. 윤식, hard to tell what the problem is by reading the statement, reading the question. You have to show your code and model simulation output. Otherwise, it is hard to tell what the problem is. So, Yunshik, yeah, why don't you, come to my office or TA's office and ask questions? I think simple problem, Yunshik. I guess very simple problem. We can fix the problem, pretty easy, I guess. Okay, 소정, 미제출인 경우랑 코드를 짰는데. 소정, I don't know. I think second, letter is better, right? No submission, right? And you are comparing no submission and submission, but submission, incomplete submission, right? So incomplete submission is, better than no submission, right? 소정. Model sim, Yunshik, no, the model sim has no problem in model sim. Okay, model sim is, commercial product. It is pretty stable simulator. So problem is your code. I'm pretty sure. Yes. Okay, any other questions? How things are working, right? So your design, Lesang, right? The data forwarding. The first one is pipelining. Instruction is going through 5 different stages: fetch, decoding, execution, memory access, write back. 5 clock cycles. Okay. Sometimes you have to store the pipe, so 6 clock cycles, right? So first you have to explain that 5-stage pipeline, that implementation, and data forwarding case, data hazard case. You have to explain, okay, at this clock cycle, at a certain clock cycle, data forwarding is happening, right? So you have to explain that also, right? Lesang. So how many forwarding you need in the example? So here that is milestone 4, right? So if you look at this, we have a lot of data dependency, right? X3, a lot of data dependencies. So if you go to milestone, so that is pipeline execution diagram, right? First instruction, you have to go through these 5, stages, and then the first forwarding is happening in clock cycle number 3, right? So in model sim, you have to show, okay, at this point, right? So that is the waveform, okay, doing this data forwarding. Clock cycle number 4, you need to forward X3 into, this, AL source, 2 AL sources, right? So that 2 data forwarding. So you have to show that, forwarding, and also this forwarding, and also store. And that would be perfect if you explain that. Also, model sim version is also important. No, it is not important. Model sim, any model sim is okay, but why are you asking the question? You are supposed to use this one, right? Do you have other model sim version? This one, 10.1D. A little bit old, but very good, simulator, commercial grade simulator. So our CPU design is actually super tiny. It looks very complicated, but actually, actual, hardware is super tiny, very, simple hardware. So this model sim can handle that kind of small, hardware design. You don't have to worry about, model sim. Model sim is perfect, I'm pretty sure. Yes, it doesn't work. Yeah, I think, depend, because we are using this FPGA, right? We are using that FPGA. It is pretty old. So latest, so this one, look at this, Quartus, right? Quartus version. Quartus version 13.1. That means, 2013, 8 years old. Quartus. The reason why we use this Quartus is because we are using this old FPGA. So latest Quartus is not supporting this old FPGA. That is why we are using this one. Also, model sim, I guess. 이제 PC가 메모리 PC가 then you have to check out MIF Yunshik, right? You have to check out MIF. This that MIF. So you are supposed to get, so you have to bring in your laptop. Otherwise, it's hard to tell what the problem is, right? I cannot see anything, right? I'm just guessing. I'm trying to I don't know, how to fix that problem without looking at your design and model sim simulation stuff. Okay, yeah. Any other questions? Yunshik, by the way, very easy problem, I guess. You are missing something, very simple thing. That is why, but I don't know what it is until I see the design. Okay, no question. Okay, let's move on. Okay, Sungo. Yes. Seung-ho, why don't you turn on your microphone? Seung-ho, that question also, if you use always, right, and passage clock, that means that implies what? That implies you want to create flip-flop, right? You want to create this flip-flop. So basically, flip-flop will be created. And if you do something like this, let's say, assuming that you want to create a PC register, right? PC plus 4, right? So if you write this Verilog code, then you are essentially creating flip-flop, right? Passage clock, that is happening. What is happening, right? This one. Reset is 1, then output is initialized. That Q is initialized, PC register. And then otherwise you are doing what? You are doing PC plus 4. That means there is an adder, okay? Adder here. And the second input is 4. PC plus 4. That is connected to the input. So if you write this passage clock, then essentially you want to create this one, a flip-flop. And then depending on your description, some other glue logic, some other logic will be added, okay, before. Okay, but if you just say just always at asterisk, then begin and end, right? Then your intention, if you do this, this is sequential logic. In Korean, 순차회로, right? 순차회로. If you write asterisk, then essentially you want to design combinational logic. In Korean, 조합회로. What is the difference? Right? Output only depends on current input, right? Combinational logic. So like this, right? ALU is one example of combinational logic, right? Output depends on only current input, right? And AND gate, right? Simple AND gate example, right? Output depends on current input. But one thing you have to note is, depending on your description, it may not generate combination logic. It may imply sequential logic. So that is some tricky point. That is why you have to understand digital logic principle. So you have to understand that principle first, then use that language to describe your target logic. Okay, so principle first, then use language to express your thought, your design, right? But Apache is not working, right? Apache is not working, right? Design, you don't understand digital logic principle, then simply use Verilog to describe hardware. That is going to be endless loop, right? You may not be able to complete your design. Some problem, then you don't know what the problem is. This is one example. You use this one. One example is this. Always, right? Let me use. So one simple example is always. Let's say y is equal to a plus b. One very simple example, begin and end. Your intention is you want to design simple adder, one adder, right? A plus b, right? So Quartus will give you that adder. A, B, and Y. Right? Simple. So what does that mean? Asterisk means whenever input changes, that is the meaning. This one is sensitivity list. Sensitivity list. What do you mean by sensitivity list? If you don't want to use this, then you can do this, A or B. Always do this. Always evaluate this adder. Always evaluate this adder when A or B, changes, right? Got changes. So that is one. A or B got changed. Then re-evaluate that adder. That is the meaning. But sometimes if you have many different inputs, A and B are input, Y output, right? So if you have many inputs, then I don't want to list all inputs in this body. That is why we want to use that asterisk. Okay. Simple, right? Simple notation. That means whenever any input changes, then output will be re-evaluated. That is combination logic, right? Output depends on current input. Output only current input, right? So that is example of generating combination logic. I think hope it will hold. Okay. And think about this code, always at this begin and end. Then you say if A is equal to A input is equal to 1. Let's say it's a 1 bit signal A. Then Y is I don't know, 0, right? Else if a 2-bit, let's say 2-bit. 1 bit is not enough. 2-bit binary, 0, 1. Let's say, okay, A, 2-bit binary, 2-bit binary, 1, 0. Okay, then Y is equal to about 1. What if you write this code? What if you write this design? We use S. Okay, S. Selection S. And then A, P. Okay, so that means whenever asterisk, whenever input changes, what are inputs in this case? Inputs are S, selection, A and B, right? Selection. Whenever S or A or B changes, re-evaluate this Y output, right? That is a description, right? But what if, but here, the problem is you do this, not problem, some input, it is not combination logic. Why? Because, all possible conditions not listed. In this case, SA is 2-bit, right? We are assuming 2-bit selection. 2-bit is 0, 1. Then you are connecting A to Y. Selection is 1, 0 and connecting B to Y. What if selection is 0, 0? Next time you got 0, 0. Then what should happen? So that condition is not listed if, right, input S is 0, 0, that condition is not listed. That means what? That means this logic should memorize last output. And it is still providing the last output if input is 0, 0, unlisted input. So that implies some memory component. In Verilog, in digital logic, right? But if you remove this, if else, so you listed all possible conditions, right? 0, 1, or other conditions, right? Meaning 0, 0, 0, 1, 0, 1, 1, or other cases. Right? Then this one, right? That means it is implying what? It is implying multiplexer, simple multiplexer, like this. If I draw Y 2-bit selection, then 0, 1, A, right? 0, 1, 0, 1, 1, right? 1, A, and the other case, B, right? B, like this, simple multiplexer. But again, if you have a specific condition, else if selection is equal to 1, 0, right? Then it is not multiplexer. It is not multiplexer, right? In addition to some multiplexer, you have some memory component. It implies memory component because that condition is not listed. 0, 0, right? 0, 0 is not listed. And 1, 1, that condition is not listed. So what if the input is 1, 1, selection is 1, 1, or 0, 0? Then it is providing last, output. Okay, last output, previous last output. So that implies latch, actually, latch. Long answer to Sungho's question. Sungho, is it answering your question? Okay. 승민, 모듈 reg 파일 코드에서 아웃풋을 RS는 okay. So what are you talking about? Let me check out. Class project. Project. Not this one. Okay. I remember I downloaded. Oh, this one. Class project. Okay. CPU. Basic module, right? Reg file. RS1 data. Assign. 승호, line number? 승민, line number? Assign? What are you talking about? Reg file, right? This is reg file, right? Register file. Assign. Output. RS data. RS1 data. This is the one? This one? Okay. 승민, we are not using this one, right? We are not using this register. There are two, register file design, right? This is the second one, right? And the first one, a lengthy version. This is the one, right? Lengthy, this one. You are using this register file, not second one, not this one. Two versions, right? Name is the same, right? If you search with this name, reg file, right? Line number 175, and then line number 15. So you are using this register file. Okay. So that is based on flip-flop, right? Flip-flop based register file design. Second one, memory based. So memory based register file design. No, you know, the Q1, the thing is, so think about that, you know, how to display. I think some of you are curious about, you know, how come you are able to display some number on 7 segment, this 7 segment, right? That hex 1, 0, 1, 2, 3, 4, right? Secret is this one. Check out RISC-V system, right? RISC-V system, and I changed the code. Okay, let me download. So let me use that complete the solution. I guess I haven't changed the solution. So this is RV32I system, right? A RISC-V system, computer system. Right? System means what? System means computer system. Not only CPU, you need at least 3 components, right? CPU, memory, and I/O devices. CPU, memory, and I/O devices. So in our system, we have two I/O devices. First one is timer. We don't use this timer. And second one is GPIO, general purpose input output. 일반 목적, you know, output I/O, right? 일반 목적 device, general purpose. Okay. So where 7 segment is connected. That 7 segment is connected to that GPIO. 7 segment, right? Why 7 segment? You have 1, 2, 3, 4, 5, 6, 7, right? 7 segment. So by turning on each segment, by segment, you can display some number. For example, you can turn on, okay, this one to display 2. Number 2, you turn on this segment, turn on this segment like this, 2. There's 2, right? And each segment is controlled by, you know, GPIO. Each segment. Right? So we have some register implemented. So by using software, right? By using this code, right? Your code using store instruction, SW instruction, you are writing something. You're writing something to your register. So if I turn on, for example, turn on that bit, you know, bit in this register, then you are, if you set this bit, then you are turning on that segment. Okay. So check out this. If you check out this CPU, right? We have memory, and then GPIO. Okay. So 7 segment is connected to that 7 segment, right? That segment is connected to this GPIO. So if you go into GPIO design, very simple actually, very simple. GPIO, right? So GPIO design, then search with some, you know, some engineering, but, you know, easy to understand. Search with, for example, hex 0. Okay, hex 0. There is a hex 0. Hex 0R. Okay, so if address is this one, not full address, but, you know, subset of the address, CPU address, right? Then this data 08, and data is written. What data? Let's say you are executing. Better to show you this milestone, you know, code right here. Like this. For example, this. So that instruction. So that instruction is displaying what? Displaying the data in X10. Okay. So X10 supposed to have what? I don't know. I think from, try to analyze this code. So that data will be written to that register, that memory location, right? X3 plus 0. Okay, that is okay. X3 supposed to contain this one. That memory location is not actually memory. It is GPIO device. So what are you confusing, right? So we have CPU, memory, IO devices. We haven't talked about accessing, IO, right? You know how to access memory, right? We have connection, right? We have connection. We have two connections, right? Instruction fetch and memory access. And also that connection is shared. That connection is shared by that IO devices. Okay, so let me remove this. It looks like this. So one address. Okay, that is connected. Okay, this one is connected to memory, and CPU is generating address for data, right? Data access, and then GPIO is also connected like this. Okay, that timer is also connected. So generating and receiving, right? And that is address. And we have also data line. This data line is connected. It is bidirectional. Sometimes you want to read, right? Bidirectional. Also bidirectional, connected. So through that connection, you can program that register. Okay. And oops. Sorry. Okay. So address, right? So I removed that. Again. Okay. We have two connections, right? Instruction fetch and data. I removed the data connection and redrew the data connection, data access connection. Address bus and data bus. Okay, address bus, data bus. Okay, so CPU, if you execute, for example, if you execute SW instruction, SW X10, no, 0, X3, then you are writing this data to that memory location. But this could be memory, this location, right? This location could be memory or this IO devices, depending on address. Then some hardware module called the decoder. Decoder is taking that address. What address? This address line. It is getting messy. Taking this address line from CPU and generate selection signal. Okay, memory. Okay, you selected memory selection. GPIO selection and timer selection. So depending on address, then one of these three will be asserted. Then you have to check out this decoder design, right? Address decoder. This is one. Depending on address, either memory or timer or GPIO is selected. Then check out this decoder design. This one is called the memory map actually. So this one is called memory map. I created that memory map, and creating memory map is super simple. So look at this Verilog description. If address is upper 19 bit, right? 31 to 13. Upper 19 bit is 0. Then memory is only selected. 0 is selected. It is it is low active signal, low active. So new terminology, right? Low active signal, meaning 0, that means it's selected. So address is this one, then okay, so this one, GPIO. Address is FFF2 something, then GPIO is selected. So that device selected. Okay, so it is called memory map. Actually, this memory map. So check out this milestone. So address, right? Address like this, F4F and 2, 4F and 2. Okay, 4F and 2. So it is creating that address. So Q1's question. Back to Q1's question. 0 되는 숫자가 안 나오셨습니다. 이 숫자 제대로 들어. So Q1, you have to first analyze this milestone 4 software, okay, and debug one by one. Probably remove everything, okay, from here to check out. It displays right number on hex 0. If it is okay, then move on to next one. Okay, turn on next one and generate MIF. Okay, put that MIF into the memory. Debugging, right? Debugging step. So you have to use your brain, intelligence, creativity. How to debug your design. I am pretty sure the problem is in your design, but if the problem hard to find the problem, then play with that. Play with that test vector. This test vector, test code. Yes, you play with that, and you try to think yourself. Think for yourself, how to debug. Okay, change software. Okay. So to do that, you have to understand, the purpose of this code. What is the purpose? Okay, this code displays some number 2, x1. This code displays this number 6 to x2 and so on. You have to first understand the operation of this code, right? Then you get some clue, what to do. Okay, any other questions? Our RISC-V system, it is toy example, but essentially it is complete computer system. It is complete computer system. It is stripped down the version. It is not like notebook computer, smartphone computer, but very small, super tiny toy example. But it is explaining almost almost everything about computer system and each operation. So we are focusing on CPU here, that CPU, but I strongly recommend you to check out that system, this system, because that will help you understand complete the complete computer, even though it is small, right? So our notebook computer, desktop computer, smartphone computer, essentially it is working the same way. So if you understand this one, then you are in very good shape, right? Understanding computer, you understand computer, and you write software, your software with more confidence. Okay, because you know what's going on. You know what's going on inside the CPU, inside the computer system, right? There's some missing concept we have to cover, but we simply don't have enough time. So last lecture, pipeline number 2, I guess. So we have to explain, I have to explain interrupt stuff. Interrupt. We have some, yeah, that interrupt stuff. That interrupt exception stuff. But we don't have time. So this PowerPoint slide is conceptually explains why you need interrupt and exception, but this is not enough, right? For concrete, in-depth understanding of that concept. But it is super important. Computer is operating based on computer is operating. Computer cannot operate without interrupt and exception. So very important. So some event happens. The interrupt is some event happens. That guy, for example, GPIO can notify that event to CPU through interrupt. So so we don't have time. So if you want to know, actually you have to know. You have to know interrupt and exception stuff and write program, write specific program for that. Next semester, I'm teaching this course, Computer Systems Design. Okay, next spring semester. So during that class, we are not doing any hardware design. Don't be scared. I'm not asking you to do any hardware design. We are going to write software only, but very low level software, assembly programming. Okay. Here, this class will cover the detail of computer system detail. In architecture course, we mainly focus on the CPU, right? We have been focusing on CPU and memory hierarchy, cache. Okay, that is the topic we are going to talk. Cache memory and TLB. And we don't have time to talk about these IO devices in this class. And interaction between CPU and IO devices. Okay, and that missing hole will be covered in this class. Okay, computer systems design. So in this class we will study smartphone CPU, ARM CPU, and play with many different IO devices, and also some internal hardware. Okay, page table creation, for example. It sounds scary, right? Page table creation and interrupt handling logic, handling program, exception handling program, those stuff. Okay. So okay. Any other questions you want to ask? And every semester, we are getting slower and slower. We are supposed to finish everything until lecture 8, but we are here. And I think we have 3 weeks left this semester. I don't think we have enough time to cover, these 4. I think we can finish only cache this semester. These 2 cache. TLB is super important, hardware component. Again, we will, that is missing, part. TLB, we don't have time to talk about TLB, but I think you have heard virtual memory, right? Virtual memory stuff. 가상 memory, right? Virtual memory is, everyone is using virtual memory. PC, computer, virtual memory. I think operating system course, I think you have heard about this technique, right? But conceptually learned that technique, right? That concept. But that is not enough, right? You need to play with, actual stuff, the virtual memory implementation. So for virtual memory, every processor has very special hardware component called that TLB. We have, cache. Cache will be discussed, but this TLB hardware component, that is, for example, Intel computer x86 Core i7. Okay, so you should know this TLB hardware component. Why the TLB is there? TLB is there to support virtual memory, but unfortunately we don't have time. We don't have time to cover this. So TLB will be discussed in COSET 321. This one also. Okay, if you don't have any question, let's move on because we are late. We are behind schedule a lot. So let's talk a little bit about cache. Okay. Okay, Kyuwon, can you please? Not much to read. Can you please?
CPU versus memory performance, Moore's law. The performance gap grows 50% per year.
Okay, thanks. Okay, thanks. Moore's law, right? You have heard about Moore's law, right? In Korean, Moore의 법칙, right? Moore의 법칙. What is that? Transistor, number of transistors. Number of transistors you can integrate in a same space. We are talking about same space. It's the same. This thumbnail sized space. Number of transistors you can integrate get doubled every 18 months. Every 18 months or 2 years. Every 18 months or 2 years. Number of transistors you can pack same space will be doubled. So what is the implication? Transistor is the basic unit of building digital logic, right? Switch. By connecting those switches, you can create something wonderful like CPU, right? So by adding more and more transistor means you can add more digital logic. For example, to support some more advanced instructions. Okay, we are not satisfied with RISC-V base instruction. We studied only 40 instructions. Okay, we can add some custom instructions. To add custom instructions, you need some transistors, right? You need AND gate, OR gate, those things. Also, utilizing those more transistors, you can think about some more good microarchitecture. Okay, pipelining is good. Okay, can you think about some other good microarchitecture like branch predictor? We discussed last time. Branch predictor is huge, taking huge hardware resources. To implement that resource, you need to implement that function. You need more transistors. Okay, so that means what? So Moore's law says number of transistors you can pack, you can integrate in the same space get doubled. And implication is performance of computer, performance of processor get doubled every 18 months. CPU performance get doubled every 18 months. Okay, so this one x-axis, year, and y performance. Performance log scale, 1, 10, 100 log scale, right? X-axis. But the problem is, memory performance. Memory technology is getting better and better, but not as good as CPU. Okay, memory performance is getting better. Getting better. This rate get doubled. Performance get doubled every 10 years. Memory performance, right? CPU and memory. CPU performance get doubled every 18 months, 1.5 years. Memory performance get doubled every 10 years. Right? That is rough trend. So that means the performance gap between CPU and memory is getting wider and wider over time. Okay, that is the problem. So this one, Seungmin, can you please? Okay, Seungho.
Memory war. CPU versus DRAM speed disparity continues to grow. The processor performance is limited by memory. This is memory war. Good memory hierarchy design is important to the overall performance of a computer system.
Okay, thanks. Same message. CPU performance and CPU and memory performance gap is getting wider and wider. So implication is it takes so much time because performance is bad, right? Comparably bad. It takes so much time to get instruction and data from memory. CPU should just wait until it gets instruction and data. Doing nothing, just wait. Right? Even though you cook up high performance CPU, CPU is not doing anything useful. Just wait. Right? That is the problem. That is called memory war. Memory war. Okay. So some animation. Okay. Consider we have so that is a computer system, right? We have used so far, right? We have CPU and memory directly connected. That is the computer model we used, right? And think about a 5-stage pipeline, okay, CPU. And assume that CPU is running at 1 gigahertz. This guy, 1 gigahertz. That means clock period. Clock period, 1 nanosecond. Clock T, right? F, 1 gigahertz, T is 1 nanosecond. Okay. And assume that main memory, to access main memory, CPU should wait 100 nanosecond. Okay. To access main memory, to get instruction, it takes 100 nanosecond. That means if you convert this time to clock cycles, 1 clock cycle, 1 clock is 1 nanosecond. So 100 nanosecond, 100 clocks, right? That is equal to 100 clocks. So CPU, to read one instruction, CPU should wait 100 clock cycles. Okay? To access data, one data from memory, CPU should wait 100 clock cycles, doing nothing, right? So pipeline execution diagram. So it looks like this. Instruction patch takes 100 clock cycles. After you get instruction, then it's very straightforward, very fast, right? Decoding, execution, memory access, write back, and you patch next instruction, right? It takes 100 clock cycles. Okay, so pipeline execution diagram looks like this. That means what? That means effectively, even though CPU is super fast, CPU super fast itself, because this guy is slow, memory is slow, CPU can effectively execute one instruction every 100 clock cycles. Okay, 100 clock cycles to execute one instruction. Right? Problem is getting worse because that performance gap is getting wider. Right? So solution. What is solution? Cache. This one. Resang.
Cache is used to reduce the large speed gap between CPU and DRAM. Cache is ultra-fast and small memory inside processor. Cache is an SRAM-based memory. Frequently used instructions and data in main memory are placed in cache by hardware. Cache is typically processed at one CPU cycle.
Okay, thanks. So the solution is this one. Solution is between CPU and main memory. You place very small, super small, but ultra fast memory called cache. Okay, very small but ultra fast memory called cache. Okay, so the hope is right? Our hope is CPU is able to get instruction and data from the cache, not from main memory. Okay, what is cache in Korean? Cache is 임시 저장소. Okay, you want to store that the data or instruction in main memory into this cache on a temporary based. Okay, store that, and then our hope is CPU get instruction and data from the cache, not from main memory. That is a hope. Okay. So cache is ultra fast but super small. How small? Typical number. Main memory. How big? Think about your computer, notebook computer. Main memory, 4 gigabyte, right? Roughly 8 gigabyte. Okay, and cache is typical number is 4 megabyte, right? 8 megabyte, around that, right? Megabyte. The unit is different. Gigabyte, main memory, megabyte. Roughly 1,000 times, right? 1,000 times smaller. This one, 1,000 times smaller. So by placing cache, and cache is super fast, so CPU can access this cache in 1 clock cycles. Hope there is also hope, but depending on CPU cache capacity and cache design, the access time is different. That access time, you have cache. So how long it takes? It takes 1 cycle. There is a hope, but 1 cycle, depending on if it is big, then you have to wait. You have to wait something like 30 clock cycles. If it is too big, 8 megabyte, but it is small, cache is small, for example, 16 kilobyte, then CPU can access this cache in 1 clock cycle, depending on the capacity and the design. So our hope is this. By placing cache, we hope that CPU can get data from the cache, so we achieve this pipeline execution diagram. Right? Every clock cycle, we want to finish one instruction. Okay, that is the hope. Let me finish this one. A cache is designed with SRAM technique. Okay, cache designed with SRAM technique, and main memory is designed with DRAM. Okay, we are not going to talk in detail, but this is the one you have to probably memorize because you don't understand this circuit detail, right? So cache is designed with SRAM technique, main memory using DRAM. Okay, and let's just stop here and continue next time. Any question though? Okay, good luck. Good luck. I hope you finish the milestone. Milestone number 5. 5 is due this Friday, right? So try to finish it. Okay, and then the last one is going to be easy. After you finish 4th, then 5th and the last one will be super easy, I guess. Right? Okay. I'll see you. I'll see you next time. Bye. Thanks. Where is control panel? Where is control panel? Zoom.